You all should be seeing we're recording now. I'm sorry about the time it took to talk about that, but I think that's the important thing to talk about. And let me now go to a different screen. Yeah, and by the way, I don't know if you guys share, do I get to see the poll, whatever you're doing? I see somebody saying about a poll. I don't see any poll.
It's on GroupMe.
Okay, thank you. As I say, I'm talking and trying to think at the same time, and that's hard to do. So there's the chat, in the group chat. Okay, since everybody's here, I think I'll take a picture of us and then we'll get to work here. So the screenshot, you don't care if you're in the screenshot, I know, as far as your pictures and stuff. So all right, I just took our attendance. And so that's out of the way, and now we can do the stuff we should be doing. Okay, so let me change this. You guys are all talkative. You ought to talk to me, but never mind. Okay, I want to close. I'm closing off the chat on one computer and trying to go to our lesson. Okay, what should appear soon on the screen? What is our lesson stuff? So, assuming you've got this, what I thought I would do today is start talking about this. Vectors real quick, hopefully, well, not too quick, but one of the questions that came up the other day after class was, what in the heck are these circles with X's and pluses in them? Okay, and that's what I want to explain first. First of all, what you do when you get more in abstract mathematics, we have addition of functions, we have addition of vectors, we have addition of numbers, different kinds of numbers. We have addition of matrices, we have addition of all kinds of different things, categories and sheaves and various other words you've probably never heard of in math. Some of them, when you find out how you define them, some additions look like multiplications. And some multiplications might look like subtractions and so on. It depends on the objects that you're talking about and how you define how you put them together. So, but we don't have very many symbols we can use that people recognize. So what mathematicians decided 100 years ago or so is they're going to define an operation of putting things together, and they're going to call it plus or times. Now, it may have nothing to do with addition or multiplication, but they're going to call it by those names just so they can have two operations. The operations may be crazy, wild, nothing to do with what usual adding numbers is about or multiplying, but we call it that just because we're used to calling things adding and multiplying. So what I don't want you to do, for example, well, let me start that sentence over. If I want to add two functions, you define how you add functions by how you add their values. So let me get off of this a second and show you something else. Just so we can, yeah, let me do this. We haven't done this very much yet, and I'm hoping you'll be able to see this. If you can't see this, tell me, please. But if I have, can you see okay? Is it, you can't, wow. You're not able to see that very well, are you?
Get the stapler ready, Dr. Brady.
I'm sorry?
To mess with the focus, remember you had to use a stapler last.
Yeah, I know. That's why I'm using my hands. The hands are, but it's too bright is the problem. And I don't know if I can change it. Is that darker? I know it's out of focus, but let me just say something real quick and then I'll figure out how to solve this problem. But I'm hoping you'll be able to read this. If I add two functions, and let me see if I can bring them up. Okay, I see how to make it better, and that's to lower the camera. All right, you all can see that, I believe.
Yes.
The two pluses are used in two different ways. One is a plus between functions, and the other is a plus between numbers, assuming that we're talking about real valued functions. So we're using the same symbol in two totally different ways. That's confusing to people who don't know too much math because they have always confused functions with function values. So when people say function, they should say function f. Sometimes people say function f of x. That's incorrect, but they don't know they're incorrect, and everybody else doesn't know they're incorrect, so everybody else thinks they understand. Anyway, what I'm trying to say here is we have a plus here is used in a function space, totally different vector space, than the numbers that you're adding on the right-hand side. So the plus on the right-hand side might be numbers. The plus on the left-hand side might be matrices. Who knows? So it's the same symbol, but different concepts. All right. So I'm going to go get off of here now and go back to the other screen. But I have to find it. Okay. So I used this times here and this plus here and put circles around it. So while you're defining something, you won't confuse a addition or multiplication of numbers with addition or multiplication of vectors. That's the whole idea. Now, as soon as you get used to the idea that you have to pay attention to the definition, not to how it looks. So when you see a plus, you automatically think addition, but it might not be addition. So you got to get used to, when you're dealing with stuff, you see a plus, you say, okay, what is that in this particular circumstance? So as soon as we realize we should do that, I take these straight crazy circles off these things. But the whole idea is to alert you to the fact we're doing something very abstract here. For example, the A and the B might be rectangles. The letter A and B might be rectangles. And adding rectangles might be rotating them. Like rotations of rectangles, like if you pin the center of a rectangle and you rotate it, that might be how we add rectangles, for example. And that's a crazy thing to talk about, but you wouldn't want to confuse that with adding numbers. So what do these things say? This says alpha, a number, times A plus B is alpha times A plus alpha times B. And if you read it like that, and that's, I think, down here a little further someplace, maybe not. I guess I didn't do it here. If you would change this and just write the alpha next to the A plus B and take off the circle, then it looks familiar. It also looks like what's in the book. Okay. What does this one say? This says if I have two numbers and add them together first and then multiply them to a vector, that's called a scalar multiplication. Numbers times vectors is called a scalar multiplication. I get the same answer as if I would first take the alpha times the A, that's a scalar multiplication, take the beta times the B, that's a scalar multiplication, and then add the vectors together. So this is like a distributive law, both of them, except we're not distributing like 3 times 4 plus 5. All those things are the same. So we know that is 3 times 4 plus 3 times 5. This is not that because these are different operations, but it looks like that. And if I would put these things next to each other without the times and without the circle around the plus, it looks like a distributive law. But I want to warn you, it's not the distributive law, it just looks like it. That's why I tried to dude it up here so you don't understand it in the sense of what the heck are these symbols. So anyway, so all we're doing here is telling you how the numbers are going to multiply to the vectors. Now, before that, what in the world is this up here? All right, we have a binary operation. You may remember from Wednesday, that means we're adding things together and getting something in the same set. It becomes a group, And a abelian group means a commutative group. This is named after Abel, but it's also called a commutative group. That means when you add things together, if you add A plus B, it's the same as adding B plus A. If you associate, if you do A plus B and then C, that's the same as doing A and then B plus C. There's an identity, which we call zero in a group. And there's inverses, which we put a minus on for a group. So what we're saying is that when I have one addition, it has those properties. Okay? Then I assume there's a second one, and it's a little different because it's defined, this is a scalar multiplication, and these are the properties of the scalar multiplication. Okay? And when we get all that done, what we have is about 8 or 9 properties of what we mean by having a vector space. Now, in the book, you don't have all this complicated stuff, and it's a little simpler, but he never really defines a vector space. He just describes it, and he talks about these being properties. Actually, they're part of the definition. Okay? We're going to have other spaces as we go through. We're going to have topological spaces, normed spaces, metric spaces. Classifications are like saying parabolas and hyperbolas and so forth. Humans like to have things classified, so when you hear what it is, you know what its properties are. When I say ellipse, you're supposed to think of a certain kind of oval. That's just the way we're programmed, the way we learn things. And so what we got to learn is what's a vector space, what's a field. The field has 2 operations, addition and multiplication. Vector spaces have addition and scalar multiplication. They're different. Now, what I do here for a few pages is to show you other properties. And again, when you say out what they say, it's not so bad. E is the identity of it's the identity vector. That's 0, 0, 0 if we're in 3 dimensions. Okay? So when I write E here, I'm talking about the identity vector. When I write 0 over here, I'm talking about the number 0. So what this says is, if I multiply the number 0 times a vector, that's scalar multiplication, I get the 0 vector. So 0 times a vector is a 0 vector. That's all that says. That's what you believe anyway. You just haven't seen it written this way. This says, if I scalar multiply -1 times a vector, I get the additive inverse. This is what you guys believe about real numbers. You want to make a negative, you stick a minus on it. But you also know to make a negative, you multiply by -1. Well, this is saying with vectors, it's the same thing. And what does this say? This says if I multiply a scalar times 0, I get 0. Okay? Now, those are the statements. And what we have here is we're calling them properties, so you have to prove them. And what you'll notice here, I'm not going to go through this in class, but it takes a while to use the properties of vector spaces to actually prove that these little simple statements are true. And that's because we're talking about very abstract objects. And therefore, you have to go exactly with what you're given by the definition. And so you can work your way through here. I hope you do. If you have questions about this kind of stuff, first of all, I hope that by what I just said, it makes this look easier. You can go through and say this out loud and it won't sound so bad. And I don't mean, when you say it out loud, I don't mean circle times, that's just hieroglyphics. I mean, write this as scalar multiplication, 0 times, and this is plus. And if you say it out loud, you're like, oh, I kind of get it, okay? So now, I give you some examples of vector spaces. You can read all about that yourself. What I want to talk about is the other little things we talk about in this class. We're going to have different kinds of what are called inner products. Now, when you guys had Calc 2 before, and when you look at section 3 in chapter 12, you have dot product. What is a dot product of 2 vectors? It's a number. Now, it's below the notes here, it's down the pages here. But how do you get the dot product? You guys are supposed to know already. You take the first elements of the ordered pair or ordered triples, you multiply the first numbers together, you multiply the second numbers together, you multiply the third numbers together, and you add it up. okay? So the dot product of two vectors is a number. Later in section 4, we're going to deal with a cross product. That's a different thing. You don't want to confuse dot products and cross products, even though it's only the first part of the two-word name that's different, but they're very different. Cross product in section 4 gives us vectors. Dot product gets us numbers. Some people in my Honors 243 class never got that figured out because I graded your test. Anyway, I hope you guys all do now. Well, this is the abstraction of a dot product. This is the properties that all dot products have, but when I abstract the idea for different things, different inner products, these are the rules. So now, the trouble with it is we run out of symbols. This represents a thing. It's like a dot product. When we have a dot product, we put a dot in between, but this is an inner product. We don't have very good ways to talk about it. It involves two objects you put together. When you put them together, you get a number. That's all what this is saying. And here are the properties. And what does this say? This says the inner product of x and y is the inner product of y and x, meaning you can turn them around. This says if I scalar multiply a vector by x and add it to the scalar multiple of y, and then take the inner product of that result with z, I could distribute it out this way. In other words, I can pick the scalar product out, and I can put the x with the z, and I can put the y with the z. That's a distributive law. And if you remember your property of dot products, that's one of the properties of dot products. This says the dot product of anything with it, the inner product of anything with itself is greater than or equal to 0. Now, what I hope you remember when you read section 3 again or for the first time, the dot product of two vectors is the square of their norm. It's the sum of the squares of the components, the coordinates. And that is a greater than or equal number. So as soon as you define a dot product, you'll know that the dot product of a number with itself is always greater than or equal to 0 if it's itself. And the dot product or the inner product is only 0 if the vector is 0. These are the properties of any inner product and are the properties of the dot product. And from that, we define something called a norm, which is the square root of this thing. And this is the inner product. Now, it's very important in my notes here. In the notes, we had some intuitive ideas in a few pages back where we said, we're going to assume we know what length and magnitude of a vector are, and we're going to try to play with them, add them and multiply them and stuff. Okay, I'm starting over again, defining what vectors are first. And now we have to define what we mean by the length of a vector and the direction of a vector. And by having an inner product or a dot product, we can talk about this thing. Now, this is like absolute value. Some books only don't use a double line, but I find kids get confused when we use a single line for both vectors and for real numbers. So I like to use double lines around a vector and single lines for absolute value around a number. Okay? Now, this thing is what we call the magnitude of the vector. It's a number, a real number. And any vector of length 1 is called a direction. Now, if you take a compass in your hand, a compass is a thing that has an arrow, as a little thing with a circle and an arrow, and it points, and it's magnetic usually. Okay, and if you're trying to find north and south and east and west, if you look down at the compass, which you hold flat, it points at something. And wherever it points, you know that's the direction. Well, in math, what we do for direction is draw a circle on the plane or on the floor in 3 dimensions, for example, or maybe we draw a sphere in 3 dimensions, depending on how you want to talk about direction. And we make an arrow from the origin to the sphere or to the disk, to the circle. And that arrow specifies a direction. So all direction is is a vector of length 1. Okay? So now we have defined both magnitude and direction, and that's what a vector is. Except it's not what a vector is. A vector is what's up above here. These are two characteristics of a vector. Well, physicists want a vector to be length and direction. We got it. Okay? That doesn't mean we did it right, but we now have for vectors length and direction. And then what we're going to do is talk about properties and stuff. So when we add two vectors, do we actually get what the physicists want for resultant forces and stuff? That's what we got to worry about. Okay? Now, we're also going to do more than the book. The book does 2 and 3 dimensions most of the time. We're going to do n dimensions, 5 dimensions, 10, 15. And the reason is not to mess you up, but once you know the difference between 2 and 3, you can talk about 15. It's just more numbers. All the rules are the same. We can't see them, but we can talk about them and we can use them. So n tuples are things that look like this. And it's just like an ordered pair or an ordered triple, but it's just more. And you normally don't have to worry about that because, as I say, it's the same rules. We just have to add more of them together. Okay? So now, what's the vector space Rn? Well, that's just these n things, n tuples we call them. And if you want to always think as n is 2 or 3, it's either pairs or triples. How do you add 2 pairs or triples together? You add the corresponding components. You guys know that already. So all we're doing is defining how you add here. See, this time I've already defined what addition and what length and direction are. And so now I'm defining addition. Okay. And what's scalar multiplication? All we do is put the thing we're multiplying into each component. You guys know that too. So this is the familiar world that's in the book. We could, instead of having n tuples of real numbers, we could change this to n tuples of complex numbers and still have the same definitions. So we could have n-dimensional complex world instead of n-dimensional real world. We're not going to do that. I'm not going to talk about it anymore. You don't want to do that, but it's the same stuff. And what I'm trying to emphasize here is the fact that these definitions can be changed. You can change the set you were talking about, and we got all the same properties. And therefore, if you learn what the properties are for this world, it will work in other worlds as well. And that is how math made great progress. Once we learned how to abstract stuff in mathematics, we got all kinds of stuff simultaneously, stuff we had not even thought about before. Okay, so here's the dot product. You know about that too. The only thing that you may not, this is using sums. When we just have 2 or 3, we probably write it out. But when you don't, you have more. So the dot product of 2 vectors is a number. You get the number, the answer, by multiplying the corresponding components together and adding all of the result. Okay? Now, the dot product is inner product. Okay, that just means once I verify, and notice it takes a little bit to verify. What I'm doing is trying to verify that that inner product I defined earlier is what a dot product is. Once I got that, then I have the properties of an inner product. Here, what's the norm in this particular problem, in this particular space? It's the sum of the squares. This is what you're used to. This is the distance you have in Euclidean spaces. And that's what we're going to use most of the time. Not always, but most of the time. So now, if I have a vector, how do I find out what its direction is? The direction, remember, is a vector of length 1. So what you do is you take your vector, you want to know what its direction is, and you multiply by the scalar 1 over the length of it. When you get done, this resulting vector is a vector of length 1, and therefore it's a direction. Now, geometrically, if you think about an arrow extending from the origin, all you do, suppose the arrow is length 5. All you do is find on the arrow what length 1 is, and that's the direction. So when I have a vector coming out of the origin, the direction is another arrow, just like this same arrow, except it's only length 1. So after you get done with that, you've got a line with 2 arrow heads on it. And one shows you what the direction is. So for example, suppose I have 1, 2, the vector over 1 and up 2. I hope you guys can picture it. I'd put it on the board if we were in class, but I don't want to go back to that blackboard you can't read, or whiteboard you can't read it. 1, 2, what's the norm of that? That's the square root of 1 square plus 2 square, that's 5. The square root of 5 is the length of the vector 1, 2. Now, we always assume the vector is starting at 0 when we're talking about its name. So when I say the vector 1, 2, you're supposed to think about an arrow that starts at 0 and goes to the point 1, 2. We're going to find out if you have an arrow that's like that, but starts at different places, what we do is subtract the components to find out what the address of the vector is. We'll talk about that a little bit later. Okay. Anyway, finding the direction is called normalizing the vector. And that's in the next line here. Now, norms have properties. And some of them are absolute value. You may remember the absolute value of the sum of 2 numbers is less than or equal to the sum of absolute values. Well, the norm has the same property. It's a very important property. It's the way we prove everything about limits, is to use these norms. This says if I have a scalar multiple of a vector, what's the length of the scalar multiple? It's just the number times the original length. So if I have 2 times a vector, how long is it? It's twice as long as the original one. That's what that says. And again, if you guys would take these things and try to read them out loud to yourself, not on a bus, because then nobody will sit next to you, but if you're someplace, and maybe not with your roommate in the room either, because they may decide you're crazier than they thought you were. But if you go someplace and say these things out loud, you'll understand them, or at least you'll come closer to understanding. This is basically saying the length of 5 times a vector is 5 times the length of the vector. Now, what happens when I multiply by -5? I'm changing the direction of the vector, but I'm not changing its length. And that's why absolute value here. So if you multiply the length, or what's the length of -5 times a vector, it's still 5 times the length of the original. And if you say it out, it's like, oh, I got that. I knew that already. You know? So what does this say? This is a much more important one in a way. The absolute value of the dot product of 2 vectors is less than or equal to the product of norms. Now, this is a very important property because from this property, we can do all of trigonometry. We can create and do everything in trigonometry from this particular little inequality. And one of the things we're going to learn here a few pages down or in the book is that the cosine of an angle between 2 vectors is the dot product divided by the product of norms. And I can probably find that, but you may get dizzy if I run down the page here. So we're going to do that soon. But anyway, this gives us angles. It doesn't look like it gives us angles, but it does. It's very important in math because we can get angles for things that don't look like arrows. Okay, and that's very important. All right, this one says when I have equality, okay, then one vector is a multiple of the other. So when I have the inequality here, now again, if you know that cosine rule from last semester, if you get equality, that says the cosine is 1. When is the cosine of an angle 1? When the angle is 0. When is the angle 0? When the 2 vectors are pointing in the same direction or in opposite directions. And when a vector is 2 vectors on the same line through the origin, one's a multiple of the other. That's what this says. So now These are the things, this is what I want you to learn. The proofs, well, it takes a while, okay? It takes a while to verify. I want you to study the proofs too, because that's where you get a real understanding. But for sure, you need to know what the proofs say, what the theorems say. And we're going to be coming back to some of this stuff all through the semester. So if you don't get a good grasp of it right now, it's okay. You're not being tested over it yet. Keep reading it. Keep trying. Keep asking. And by the way, I'd be happy to know if you guys, have you got to page 35 yet? Are you still on page 1? I mean, it might be that some of you can't read. If that's the case, it's not my fault. Okay? If you can't read, well, okay, I'll feel sorry for you, but I'm not going to pass you. Okay, how do we measure distance in a vector space? We take the norm of the difference of the vectors. Here are distance properties. Okay, so it's 11 after. I'm not going to have too much time, so I want to get to this thing down here because you may wonder what in the world is all this about. Okay, first of all, there are some standard vectors that we name. And 1, that's like out the x-axis when we get the x-axis, which we haven't got yet. In the notes, I don't know what an x-axis is yet. In the book does, but I don't know that yet. Anyway, these numbers are vectors on the arrows point out along the axes when we get the axes defined. And they're called standard basis vectors. They're called standard Cartesian coordinate vectors. It's called standard Euclidean vectors. They all mean length 1. They all are directions. And we'll get familiar. And a lot of times in engineering, they like to use I, J, and K for these. In math, because we might have 55 of them, we like to use E1 to E55. But for most of the time, you and me will have I and J and K, because that's what the book does, and that's what you guys see in engineering, those of you who are there. Okay, now, I started out the other day by telling you that I'm bothered by the fact that people put straight lines on in chapter 12 and tell you here's a coordinate system when we don't yet know what a straight line is until section 5. Okay, so I'm going to start talking now about what a straight line is in these notes. And what's the word straight mean? Okay, are all lines straight and stuff? And well, who knows? So when do we know that 2 points make a line? In other words, I want to define what I mean by the line through 2 points. Now, I'm not thinking of arrows now. I'm thinking of the points in the tuples. I may not be thinking of pictures in space or something, but I'm thinking of pairs or triples or quadruples. That's why you see this right here. So when do we have a line through 2 points? The answer is when you take a third point in that same set, the set you're calling a line. And one of these three things has to happen. Okay, now this is complicated sounding. It's not complicated at all. It just sounds like that. So I'm going to have to go back to drawing a picture on a screen here in a second for you. And so hopefully if we can see this now, or maybe I'll raise it a little bit. I can't, if I try to lower the webcam, I'll kill something. Anyway, if I have 2 points and I want to talk about what's the line between the 2 points. Now, of course, I'm going to draw something like this because I kind of know what the line is between 2 points. But how do you define it mathematically? You take a third point. Now, I'm hoping you all see, can everybody see this? Anybody not be able to see this? I'm holding it in my hand, so it's not very steady. If I take a third point in these points, and right now, by the way, let me do one more thing. Right now, my third point might be over here. Sorry. My third point might be here. That wouldn't actually end up on the line. We know that just because we know about lines a little bit. But right now I'm saying, suppose I take a third point. When is that third point going to be part of that definition? Well, what I'm hoping, the reason I'm doing this right now is to show you if I take a third point, it could be here, it could be here or it could be over here, right? As soon as I put a third point in here, it could be in 3 different places. Now, it could actually be one of the 2 points as well, but we're assuming it's a different point. So in order to talk about what goes on with a point on the line, I have to have 3 different definitions. What if the point happens to be over here that I take? Then this distance here plus the distance here has to equal the whole distance. And that's one of the 3 statements on that other stuff in your notes. On the other hand, if the point happens to be here, then it's this distance plus this distance to give you the whole distance. Now I'm going to go back now to the other thing, and hopefully I can get this going for us quicker. Hello, where is the thing? Here we go. Okay, these 3 things say the distance from A to B plus the distance from B to X is the distance from A to X. That's when the X is outside A and B. This one says the distance between A to X and distance between X and B is the distance between A and B. That says the X is between the 2. Now, by the way, if it's not on the line, it's not between the 2, but that's another, see. Now, with that picture I had a minute ago, when I have one point that's not on the line there, the third point, if you drew line segments between the 3 points, what you would get is an inequality. So a definition of when you have a line has to do with when one of these 3 situations is true. Okay, that's what you mean by a straight line. Now, this is a hard, when you do this, and when I do this stuff first, it takes me a while to prove stuff because you got 3 different things you got to verify all the time. But what are the, so from now on for a little bit, let's just talk about what the theorem says, not what the proofs are. The theorem says, suppose I take a bunch of points and they're like X, EK. Now, XE1 is like X0, 0. That's a point on the X-axis. Is the X-axis a straight line? That's the question. The theorem says the X-axis is a straight line. That's what the theorem says. 2. It takes a while to prove, notice. What's theorem 3? If I have a point and 0, what's the straight line through the 0 and a point? Well, it's all multiples of the point, scalar multiples. You guys know this stuff already. If I have a line passing through a point, you know it's equations like y equals mx, for example, in 2 dimensions. We don't know what it is in 3 dimensions yet. That's what I'm telling you about now. Because in 3 dimensions, we have vectors, and we take scalar multiples of vectors to get lines. Now this just says the line from 0 to A, so I have some notation. But again, to prove that, well, it takes a little less time because I already did the other one, but it takes a little proof. Now, so, and you can read this later, but let's look at number 4. Well, number 4 says, if I take a point on the line between 0 and A, or through 0 and A, then A is on the line through 0 and C. What you want to do is think out what I'm saying. If I have a point 0 and I have a point out in the plane somewhere, and I want to say a third point's on that line, well, I could also describe the line using the third point instead of the second point. What this says, if you think about it, is if I have a point on the line through 0 and A, then A is on the line through 0 and C. It makes sense. What's theorem 5 say? Every non-zero point on the line has a direction which is plus or minus the direction of the point A. In other words, lines on the same points on the same line have the same direction if we're going through 0. So lines that go through 0, any 2 points on a line through 0 has the same or opposite direction. Now I'm running out of time because it's 20 after, But these theorems, if don't worry about the proofs as much. I want you to worry about the proofs, but lesser. Try to understand what we're trying to tell you here. And then you'll see why I had to go to all this trouble to describe a line. And we finally come down. This is the equation that's in the book in section 5. The equation of a line through 2 points is called a parametric equation. You guys learned it in Calc 2. So we get to that because we've defined what a line is. Okay? Now, I've been doing a lot of talking. Have I made any sense? What I'm going to do, by the way, right now, is get off of this and stop the recording.